Imagine waking up tomorrow and discovering that everything you've ever believed about reality is wrong. Not slightly wrong. Completely wrong. The distance between Earth and the Moon. An illusion. The billions of light years separating galaxies. Possibly an illusion. Even the space between you and the screen you're watching right now might not actually exist in the way you think it does. That sounds like science fiction. But some of the world's most respected physicists have spent decades wrestling with an unsettling possibility. What if space itself isn't fundamental? What if reality is built from something deeper? And what if the strangest phenomenon ever discovered, quantum entanglement, is the clue that's been hiding in plain sight all along? Because quantum entanglement allows two particles to remain connected across vast distances. Change one. And the other seems to know instantly. No signal. No communication. No travel through space. Just connection. A connection so bizarre that Albert Einstein himself called it spooky action at a distance. But what if Einstein was wrong about what made it spooky? What if the real mystery isn't how information travels through space, but why we assume space is there in the first place? And if that's true, the implications are terrifying. Because the universe may be far stranger than anyone imagined. And by the end of this documentary, you'll see why some physicists believe that reality itself may emerge from invisible relationships hidden beneath space and time. But to understand how we got here, we need to begin with one of the greatest scientific revolutions in human history. A revolution that shattered reality. And we're only getting started. For thousands of years, humans thought the universe was simple. Objects existed. Space separated them. Time flowed forward. Cause created effect. Reality felt obvious. When you throw a ball, it moves through space. When the sun rises, time passes. Everything seems intuitive. Then quantum physics arrived. And everything fell apart. Over the next 2 hours, we're going on a journey from the birth of quantum mechanics to the shocking experiments that proved Einstein wrong, to the modern theories suggesting that space itself may emerge from quantum entanglement. Along the way, we'll explore black holes, information paradoxes, hidden dimensions, quantum teleportation, and one question that may redefine reality forever. What if the universe isn't made of things? What if it's made of connections? And the deeper physicists investigate, the more unsettling the answer becomes. Because the real story isn't merely about tiny particles. It's about the nature of existence itself. Let's begin. Chapter 1, The Universe That Made Sense. Picture yourself standing in Europe during the late 1600s. The scientific revolution is transforming the world. And one man is changing humanity's understanding of reality forever. Isaac Newton. Newton's universe was elegant, predictable, mechanical. The cosmos behaved like a gigantic clock. Every object had a position. Every motion had a cause. Given enough information, you could predict the future. The moon orbited Earth. Planets orbited the sun. Apples fell from trees. Everything obeyed universal laws. For centuries, this view dominated science. And honestly, it worked incredibly well. Ships crossed oceans. Engineers built bridges. Astronomers predicted eclipses. Physics seemed nearly complete. Many scientists believed only minor details remained to be discovered. But hidden beneath this confidence was a problem. A tiny crack in reality. One that would eventually explode into a revolution. Because when scientists began studying light and atoms, they found behavior that made no sense at all. The universe wasn't acting like a clock. It was acting like something else entirely. And the first clues appeared in places nobody expected. Inside the atom itself. But what scientists discovered there would trigger one of the greatest crises in scientific history. And the consequences are still unfolding today. Chapter 2, The Cracks in Reality. At the dawn of the 20th century, physicists faced a nightmare. Their equations were failing. Experiments kept producing impossible results. The classical universe was breaking down. One of the biggest mysteries involved light. Light behaved like a wave. At least, that's what everyone believed. But certain experiments suggested something shocking. Light sometimes behaved like particles. Not occasionally. Not metaphorically. Actually. This wasn't supposed to happen. Waves and particles were fundamentally different concepts. A wave spreads. A particle stays localized. Something couldn't be both. Yet experiment after experiment suggested exactly that. Then came Max Planck. Then Niels Bohr. Then Werner Heisenberg. Then Erwin Schrödinger. Each discovery pushed reality further into absurdity. Electrons didn't have precise positions. Particles existed as probabilities. Observation seemed to affect outcomes. The universe suddenly resembled a cosmic mystery novel. And nobody understood the ending. Physicists could predict experimental results with incredible accuracy. But understanding what was really happening, that was another story. Even today, more than a century later, physicists still debate what quantum mechanics truly means. And among all its strange features, one phenomenon stood above the rest. A phenomenon so bizarre that even the scientists who discovered it struggled to believe it. Quantum entanglement. The phenomenon that would eventually force humanity to question the existence of space itself. But before we get there, we need to understand why Einstein hated it. Because nobody fought quantum entanglement harder than him. And for a very good reason. Chapter 3, Einstein's Greatest Battle. Albert Einstein helped create quantum physics. Yet he spent decades fighting it. That sounds contradictory. But Einstein wasn't rejecting the mathematics. The equations worked. The predictions worked. The experiments worked. What troubled him was something deeper. Reality itself. Einstein believed the universe should make sense. Events should have causes. Objects should possess properties whether or not someone observes them. Reality should exist independently of measurement. Quantum mechanics seemed to violate all of these principles. Then things got worse. In 1935, Einstein and two colleagues, Boris Podolsky and Nathan Rosen, published one of the most famous papers in physics. Today it's known simply as the EPR paper. And it introduced a paradox. Imagine two particles interacting. Then separating. According to quantum theory, they could remain linked. Connected. Entangled. Measure one particle. And you instantly know something about the other. No matter how far apart they are. Even if they're on opposite sides of the galaxy. Einstein found this ridiculous. Nothing should influence something else faster than light. Special relativity forbade it. Space imposed limits. Distance mattered. Or at least it was supposed to. Yet quantum mechanics seemed to ignore those limits entirely. Einstein believed the theory must be incomplete. There had to be hidden information. Hidden variables. Something deeper restoring common sense. Most physicists agreed with quantum mechanics. Einstein remained skeptical. The debate continued for decades. And then an unexpected development changed everything. A quiet physicist from Northern Ireland asked a simple question. What if Einstein was wrong? The answer would shock the scientific world. Chapter 4, The Man Who Tested the Impossible. In the 1960s, physicist John Bell confronted a challenge. How could anyone experimentally test whether Einstein was right? For decades, the argument seemed philosophical. Interesting. But untestable. Bell changed that. He developed a mathematical framework now known as Bell's theorem. And it transformed physics forever. Bell showed that Einstein's hidden variable explanation made specific predictions. Quantum mechanics made different predictions. Meaning there was finally a way to test reality. Not through debate. Not through philosophy. Through experiment. It was an astonishing breakthrough. For the first time, scientists could directly ask nature. Is reality local? Or is quantum mechanics correct? Years later, increasingly sophisticated experiments were performed. Again and again. Across decades. The results kept arriving. And every time they pointed in the same direction. Einstein's view lost. Quantum mechanics won. Reality truly behaved as if entangled particles shared connections that transcended ordinary space. Not metaphorically. Not theoretically. Experimentally. Verified. Repeatedly. Relentlessly. The universe was telling us something. But physicists still couldn't agree on what. Because while Bell's experiments destroyed one mystery, they created an even larger one. If entanglement is real, what exactly is being connected? And where does that connection exist? The answer may be far stranger than anyone imagined. Because some physicists began wondering whether space itself emerges from entanglement. And that idea changes everything. Chapter 5, What Entanglement Really Means. Let's slow down for a moment. Because this is where many explanations become misleading. Entanglement does not mean particles send secret messages. It does not mean faster-than-light communication. And it doesn't mean one particle physically reaches across space. The truth is subtler. And arguably even stranger. Imagine two coins that somehow share a hidden relationship. Not hidden information. A hidden connection. When you examine one coin, the state of the entire system becomes defined. The second coin isn't receiving information. The relationship was already there. But quantum reality goes far beyond ordinary analogies. Because before measurement, the system doesn't behave as though outcomes were secretly predetermined. Experiments strongly suggest the possibilities themselves remain fundamentally undefined. That's the disturbing part. Reality may not possess definite properties until interaction occurs. And entanglement links these uncertainties together. Physicists describe entangled systems using a single mathematical object. Not two separate objects. One system. One description. Even if the particles are separated by enormous distances. Think about that. Mathematically speaking, the universe doesn't always care about spatial separation. Two distant particles can behave more like one system than two independent things. And if mathematics keeps treating them as fundamentally connected, perhaps space isn't telling the full story. Perhaps separation is not as real as it appears. That possibility sounds outrageous. But the next chapter takes us into a place where physicists are seriously considering exactly that. The world of emergent space. And the implications are staggering. Chapter 6, The Day Space Stopped Being Fundamental. Imagine you're standing on a beach. The ocean stretches endlessly toward the horizon. Waves crash against the shore. Everything appears smooth and continuous. But if you zoom in far enough, the smooth water disappears. What seemed continuous was actually made of countless individual molecules. The ocean emerges from something deeper. Now imagine the same thing is true for space itself. What if space is not fundamental? What if it emerges from something deeper? This idea sounds radical. But over the last few decades, some of the brightest physicists on Earth have begun taking it very seriously. Because quantum entanglement kept pointing toward a disturbing possibility. The mathematics worked too well. Again and again, calculations suggested that relationships between particles might be more fundamental than the distances separating them. Think about what that means. For centuries, space was considered the stage where reality unfolds. Objects exist inside space. Events happen inside space. Galaxies move through space. But what if we've had it backward all along? What if space emerges from the connections between things? Not the other way around. This wasn't merely philosophical speculation. Unexpected clues started appearing in one of the most extreme environments in the universe. Black holes. And black holes were about to create one of the biggest crises in physics. A crisis that would force scientists to reconsider everything they thought they knew about reality. Chapter 7, The Black Hole Paradox. Black holes are terrifying. Not because they destroy matter, but because they seem to destroy information. And information is supposed to be indestructible. To understand why this became a problem, imagine throwing a book into a black hole. The book contains information. Words. Ideas. Patterns. Memories. According to quantum physics, information should never truly disappear. It can change form. It can spread out. But it cannot be erased from existence. Yet black holes seem to do exactly that. Anything crossing the event horizon vanished forever. Information included. Then, in the 1970s, everything became even stranger. A young physicist named Stephen Hawking made a discovery that shocked the scientific world. Black holes aren't completely black. They glow. Very slowly. Very faintly. But they radiate energy. Today we call this Hawking radiation. And it created a nightmare. Because if black holes emit radiation, they eventually evaporate. Over unimaginable periods of time, they disappear completely. So now physicists faced an impossible question. What happens to the information? The black hole vanishes. The information vanishes. But quantum mechanics says information cannot vanish. Both ideas couldn't be true simultaneously. Something had to give. For decades, the paradox haunted theoretical physics. And eventually, solving it would lead researchers toward a revolutionary realization. Entanglement wasn't just a strange feature of reality. It might be the foundation of reality itself. Chapter 8, The Holographic Universe. Now we're entering territory that sounds impossible. Yet some of the world's leading physicists believe it may describe reality. Imagine a hologram. A three-dimensional image encoded on a two-dimensional surface. You've probably seen holographic images on credit cards or security labels. The image appears three-dimensional. But the information exists on a flat surface. In the 1990s, physicists discovered something extraordinary. Certain mathematical descriptions of gravity seemed equivalent to theories without gravity existing on lower-dimensional boundaries. At first this sounded absurd. But the equations kept working. Again. And again. And again. Eventually, a startling possibility emerged. What if our universe behaves like a hologram? What if the three-dimensional world we experience emerges from information encoded elsewhere? This became known as the holographic principle. And while the details are highly technical, the implications are astonishing. The universe may not be fundamentally three-dimensional. The reality we experience could emerge from deeper informational structures. But here's where things become truly bizarre. Entanglement kept appearing at the center of these theories. As if the geometry of space itself was somehow woven from quantum connections. And one physicist would take that idea further than almost anyone before him. His name was Juan Meldacena. And his work would change modern theoretical physics forever. Chapter 9, The Discovery That Shook Physics. In 1997, Juan Meldacena published a paper that many physicists consider one of the most important discoveries of the modern era. The technical details are complicated. But the basic idea is extraordinary. Two completely different theories appeared mathematically identical. One described gravity in a higher dimensional space. The other described quantum fields without gravity on a lower dimensional boundary. Different descriptions. Same physics. This became known as the AD/CFT correspondence. And it quickly transformed theoretical physics. Because suddenly, researchers had a powerful new way to explore the relationship between gravity, quantum mechanics, and information. But hidden inside these equations was something unexpected. The geometry of space seemed deeply connected to patterns of entanglement. The more physicists investigated, the stranger things became. Space itself appeared linked to information. Linked to connectivity. Linked to quantum relationships. It was as if geometry emerged from entanglement. As if distance itself was being generated by invisible quantum connections. At first, many scientists viewed this as a mathematical curiosity. Then evidence began accumulating. And the implications became impossible to ignore. What if entanglement literally creates space? Not metaphorically. Literally. If true, it would mean that what we call distance emerges from quantum information. And that possibility leads directly to one of the strangest ideas ever proposed. Wormholes. Chapter 10, ER equals EPR. Sometimes, science produces ideas so strange they sound fictional. This is one of them. In 2013, physicists Juan Meldacena and Leonard Susskind proposed a remarkable possibility. Perhaps entanglement and wormholes are connected. The idea became known as ER equals EPR. The initials refer to two famous concepts. Einstein-Rosen bridges. And Einstein-Podolsky-Rosen entanglement. Wormholes and entanglement. Two mysteries. One reality. According to this proposal, entangled particles may be connected through microscopic wormholes. Not traversable wormholes. Not science fiction tunnels. Something far more subtle. A deep equivalence hidden within the mathematics of reality. At first glance, the proposal seems impossible. But the equations revealed surprising connections. Again and again. Different branches of physics kept converging toward the same conclusion. Entanglement wasn't just another quantum phenomenon. It appeared woven into the fabric of spacetime itself. And if spacetime emerges from entanglement, then something astonishing follows. Destroy enough entanglement. And space itself begins to disappear. Let that sink in. The universe around you may depend on invisible quantum relationships. Break those relationships. And geometry collapses. Space dissolves. Distance loses meaning. The implications are difficult to overstate. Because they suggest that reality is not built from objects. It's built from connections. And what happens next takes us even deeper into the rabbit hole. Because physicists began asking a terrifying question. If space emerges from entanglement, what emerges from space? Or put another way, what lies beneath reality itself? So far we've discovered something extraordinary. Quantum entanglement may not simply exist within space. Space itself may emerge from entanglement. But we've only scratched the surface. Because in the next part, we'll explore how physicists are literally reconstructing spacetime from quantum information. Why reality may resemble a giant cosmic network. How the universe might function like an unimaginably advanced quantum computer. And the unsettling possibility that consciousness, information, and reality are connected in ways we barely understand. Because what most people don't know is that the deeper scientists investigate quantum entanglement, the less fundamental reality appears. And what waits beneath it may be stranger than anything humanity has ever imagined. To be continued. Chapter 11, Rebuilding Spacetime from Scratch. Imagine waking up inside a house. You see walls, windows, doors, furniture. Everything appears solid and complete. But then someone reveals a shocking truth. The house wasn't built from bricks. It wasn't built from wood. It wasn't built from concrete. It was built entirely from relationships. Connections. Patterns. Information. At first, that sounds impossible. Yet this is remarkably close to what some physicists are attempting to do with reality itself. They're trying to rebuild spacetime from quantum entanglement. Not describe it. Not assume it exists. Actually reconstruct it. And surprisingly, it's working. Over the last 2 decades, researchers have discovered that changing patterns of entanglement changes the geometry that emerges from the equations. Increase certain entanglement relationships, and regions of space appear more connected. Reduce those relationships, and those regions begin drifting apart. It's almost as if entanglement acts like the invisible stitching holding spacetime together. Picture a giant cosmic fabric. Not made of matter. Not made of energy. Made of information. Made of quantum relationships. Every connection contributes to the structure we experience as reality. And when physicists run the mathematics, something astonishing happens. Geometry begins appearing naturally. Distance emerges. Shape emerges. Spacetime emerges. Without assuming space exists beforehand. Think about how radical that is. For centuries, space was the starting point. Now it may be the result. A consequence. An emergent phenomenon. But if spacetime can be reconstructed from entanglement, then what exactly is entanglement? Why does it possess such incredible power? And why does the universe seem determined to place information at the center of everything? The answer may reveal what reality is truly made of. Chapter 12, The Universe as Information. Let's perform a thought experiment. Imagine removing every object from the universe. Every planet. Every star. Every atom. Every particle. Everything. What remains? Most people would answer. Space. Empty space. A vast cosmic stage waiting to be filled. But some physicists believe that's wrong. Because what if information is more fundamental than space? The idea sounds abstract. Yet information has become increasingly important in modern physics. Not just useful. Fundamental. John Wheeler, one of the 20th century's greatest physicists, proposed a famous phrase. It from bit. 3 simple words. Yet they carry enormous implications. According to Wheeler, physical reality ultimately emerges from information. Not matter. Not energy. Information. Think about your computer. Everything on the screen appears different. Photos. Videos. Games. Documents. Yet underneath, it's all information. Different arrangements of bits. Could reality work the same way? Could stars, galaxies, black holes, and even spacetime itself emerge from deeper informational structures? Increasingly, some researchers believe the answer may be yes. And entanglement appears to be one of the mechanisms that organizes that information. Not unlike how relationships between neurons create thoughts inside a brain. Or how relationships between individuals create societies. The individual components matter. But the connections matter even more. Because connections create structure. Connections create complexity. Connections create reality. And if that's true, then the universe may not be a collection of things. It may be a network. A gigantic informational network beyond anything humanity has ever imagined. But what does that network actually look like? And how can something as abstract as information create something as concrete as space? That's where things become truly fascinating. Chapter 13, The Cosmic Web Beneath Reality. Look at a map of airline routes. At first, it seems chaotic. Thousands of flights. Thousands of destinations. Endless complexity. But zoom out. And patterns emerge. Connections. hubs, networks, structure. Now imagine doing the same thing with reality itself. Some physicists believe the universe resembles an unimaginably vast network of quantum connections. Nodes connected to nodes. Relationships connecting relationships. Information interacting with information. And from those interactions, space-time emerges. One useful analogy comes from the internet. When you send a message online, you don't think about the countless invisible connections carrying information across the globe. You simply experience the result. Likewise, we experience space. But perhaps space is the result of deeper informational processes hidden beneath our perception. The visible world might be like the interface of a computer. Useful. Practical. But not fundamental. The deeper reality may consist of quantum relationships operating beyond ordinary intuition. This idea has inspired new mathematical frameworks. Tensor networks. Quantum error-correcting codes. Entanglement geometries. At first glance, these concepts appear highly technical. Yet they all point toward a similar conclusion. Reality may emerge from connectivity. Not location. Connection before position. Relationship before distance. Information before geometry. And if that's true, then one of humanity's most basic assumptions may be wrong. Distance may not be fundamental. Distance may simply measure how entangled things are. Think about that for a moment. Two regions appearing far apart might merely be weakly connected. Two regions appearing close might be strongly connected. Space itself becomes a map of information. And if space can emerge this way, what about movement? What about communication? What about teleportation? As strange as it sounds, quantum teleportation may offer some clues. And what scientists discovered is almost impossible to believe. Chapter 14, Quantum Teleportation is Real. When people hear the word teleportation, they imagine science fiction. People disappearing. Instant travel. Starships. Transporters. But quantum teleportation is real. And it has already been demonstrated experimentally. Now, before we continue, let's clarify something important. Quantum teleportation does not transport objects. It doesn't move people. At least not with current physics. Instead, it transfers quantum states. Information. Yet even that is astonishing. Scientists have successfully teleported quantum information across increasing distances. Laboratories. Cities. Satellites. Thousands of kilometers. The process relies on entanglement. Without entanglement, quantum teleportation becomes impossible. And this is where things become interesting. Because teleportation suggests something profound about reality. Information isn't always tied to location in the way we assume. In ordinary life, moving information requires movement through space. But quantum mechanics keeps challenging that intuition. Again and again. The deeper researchers investigate, the more reality appears centered on relationships rather than positions. Connections rather than locations. Information rather than objects. And every discovery seems to reinforce the same message. Space may not be the foundation. Space may be the consequence. But if information and entanglement are so important, could they explain another great mystery? Time itself. Because some physicists have begun asking an even more unsettling question. What if time is emergent too? Chapter 15, The Possibility that Time is an Illusion. Space is one thing. Time is another. Or at least that's what most of us assume. Every second of your life feels real. The past happened. The future hasn't happened. The present is unfolding right now. Simple. Obvious. Yet modern physics tells a different story. When physicists write down some of their deepest equations, time begins behaving strangely. In certain formulations of quantum gravity, time seems to disappear entirely. Not slow down. Not distort. Disappear. The equations still work. Reality still exists. But time isn't fundamental. This creates a profound mystery. If time isn't fundamental, where does our experience of time come from? Why does the universe appear to flow from past to future? One possibility is that time emerges from deeper informational relationships. Just as temperature emerges from molecular motion. Just as waves emerge from water molecules. Just as spacetime may emerge from entanglement. Time itself may emerge from changes in information. This idea remains highly speculative. Yet it's receiving increasing attention. Because whenever physicists try combining quantum mechanics and gravity, space and time both seem less fundamental than expected. Something deeper appears to exist beneath them. Something more primitive. Something more abstract. Something involving information and entanglement. If true, the implications are staggering. The universe we experience may resemble a shadow. A projection. An emergent layer arising from deeper structures we rarely perceive. And the further scientists explore, the stranger the picture becomes. Because next we'll encounter a possibility that sounds almost impossible. The universe itself may behave like a giant quantum computer. And if that's true, reality may be processing information in ways we are only beginning to understand. We've traveled a long way. From quantum entanglement to emergent spacetime, to the possibility that information lies beneath reality itself. But the journey is about to become even stranger. Because in the next part, we'll explore how the universe might function like a quantum computer. Why black holes may be nature's ultimate information processors. How reality could emerge from computation. The shocking limits of human perception. And the growing suspicion that what we call the physical world is only a tiny fragment of a much deeper reality. Because what most people don't realize is this. Every answer physicists uncover seems to raise even bigger questions. And some of those questions challenge the very meaning of existence itself. To be continued. Chapter 16, Is the Universe a Giant Quantum Computer? Imagine for a moment that the universe is not a machine. Not a collection of objects. Not a giant clockwork system. But a computation. A process. An endless flow of information being transformed from one state into another. At first, this sounds like science fiction. Yet some of the most respected physicists and computer scientists have seriously explored this possibility. Because the deeper researchers study reality, the more it seems to behave like information processing. Think about it. Every interaction changes information. Every particle interaction can be described mathematically. Every physical law transforms one state into another. Reality appears to be constantly computing its next moment. Seth Lloyd, a physicist at the Massachusetts Institute of Technology, once proposed a remarkable idea. The universe is a quantum computer. Not a computer built inside the universe. The universe itself. Every particle participates in the computation. Every interaction contributes to the result. Every event becomes part of an unimaginably vast information processing system. And if spacetime emerges from quantum information, then computation may help generate reality itself. This idea raises fascinating questions. What exactly is being computed? Why does the computation exist? Who, or what, determines the rules? No one knows. But the possibility becomes increasingly difficult to ignore. Especially when we examine the most extreme information processors in existence. Black holes. Because black holes may reveal what reality is doing behind the scenes. And what they suggest is astonishing. Chapter 17, Black Holes, the Ultimate Information Machines. Imagine compressing an entire mountain into something smaller than a grain of sand. The density would be unimaginable. The gravity overwhelming. Now keep compressing. Eventually, you create something extraordinary. A black hole. For decades, black holes appeared to be cosmic dead ends. Places where information vanished forever. But modern physics tells a very different story. Increasingly, black holes appear less like destroyers of information and more like information storage devices. Every object falling into a black hole contributes information. Mass. Energy. Quantum states. Structure. Patterns. And surprisingly, physicists discovered something strange. The information content of a black hole appears related to its surface area. Not its volume. Its surface. This observation became one of the foundations of the holographic principle. And it hints at something profound. Reality may encode information very differently than our intuition suggests. Black holes became laboratories for testing ideas about information, entanglement, spacetime, and quantum gravity. Again and again, researchers found the same thing. Information appears fundamental. More fundamental than matter. More fundamental than geometry. Perhaps even more fundamental than space and time themselves. And if that's true, then reality may be built from informational structures operating beneath everything we experience. But there's another mystery we need to confront. A mystery much closer to home. Because even if reality is far stranger than we imagined, we still have to ask. Can our brains perceive it accurately? The answer may be deeply unsettling. Chapter 18, Your brain is not showing you reality. Right now, look around you. Everything feels real. Solid. Continuous. Reliable. Yet neuroscience reveals something extraordinary. Your brain is not directly experiencing reality. It's constructing a model. A simulation. An interpretation. Light enters your eyes. Electrical signals travel through neurons. Your brain reconstructs what it believes exists outside. The colors you see. Interpretations. The sounds you hear. Interpretations. Even your sense of space may be an interpretation. Evolution did not design your brain to perceive objective reality. Evolution designed your brain to survive. Those are not the same thing. Imagine a computer desktop. You see folders. Icons. Buttons. Documents. But none of those things literally exist inside the computer. They're interfaces. Simplified representations hiding deeper complexity. Some researchers believe perception may function similarly. What we experience could be a user interface. An efficient representation rather than direct access to ultimate reality. If that's true, then space itself might be part of the interface. A useful construct generated by minds interacting with deeper informational structures. And suddenly, the idea that space emerges from entanglement becomes less absurd. Because perhaps our brains evolved to perceive relationships as locations. Information as geometry. Connectivity as distance. What we call reality may simply be the best approximation available to biological creatures. But if our perception is limited, how much of reality remains hidden? The answer may be far more than we think. Chapter 19, The Invisible Universe. Consider this. Everything you can see. Every star. Every planet. Every galaxy. Every cloud of gas. Every atom in your body. Represents only a tiny fraction of the cosmos. Astronomers estimate that ordinary matter accounts for roughly 5% of the universe. 5%. The remaining 95% consists of dark matter and dark energy. And we still don't fully understand either one. Think about that. Humanity's best theories explain only a small portion of reality. The vast majority remains mysterious. Invisible. Unknown. This realization is humbling. But it's also revealing. Because history repeatedly teaches the same lesson. Reality is stranger than appearances suggest. The Earth isn't flat. The Sun doesn't orbit us. Matter isn't solid. Space isn't empty. And now physicists are questioning whether space itself is fundamental. Every generation discovers deeper layers beneath what seemed obvious. Perhaps we're witnessing another such moment. Perhaps quantum entanglement is revealing a hidden architecture beneath reality. An architecture we are only beginning to glimpse. And if that's true, the implications extend far beyond physics. Because they affect one of humanity's oldest dreams. The search for a theory of everything. Chapter 20, The Search for the Final Theory. For more than a century, physicists have pursued a single goal. A theory of everything. One framework capable of explaining all physical phenomena. One set of principles underlying every force. Every particle. Every interaction. Every law of nature. So far, we have two extraordinarily successful theories. Quantum mechanics. And general relativity. Each works brilliantly. Yet they refuse to fully cooperate. Quantum mechanics governs the microscopic world. General relativity governs gravity and the cosmos. Both are correct. Yet combining them remains one of the greatest challenges in science. This conflict has driven generations of researchers. String theory. Loop quantum gravity. Holography. Quantum information theory. Countless approaches. Countless breakthroughs. Countless frustrations. And increasingly, one idea keeps resurfacing. Entanglement. Not as a side effect. Not as a curiosity. But as a foundation. A potential bridge connecting quantum mechanics and spacetime. A clue pointing toward deeper reality. Could entanglement be the missing ingredient? Could the universe emerge from information? Could spacetime itself be the product of quantum relationships? No one knows for certain. But the evidence continues to grow. And the more scientists investigate, the harder it becomes to dismiss. Yet perhaps the most unsettling implications are not scientific. They're philosophical. Because if space is emergent, if time is emergent, if reality arises from information, then some of our deepest assumptions about existence may need to be rewritten. And that's where our journey heads next. Toward the most terrifying implications of all. Chapter 21, The Terrifying Possibility. Let's pause and consider everything we've learned. Entanglement connects distant particles. Space may emerge from entanglement. Information may underlie reality. Time may not be fundamental. Perception may function as an interface. Individually, each idea is remarkable. Together, they become revolutionary. Because they point toward a startling conclusion. The world you experience may not be the foundation of reality. It may be an emergent layer. A higher-level description. A useful approximation. Think about a hurricane. The hurricane is real. You can measure it. Observe it. Experience its effects. Yet the hurricane is not fundamental. It's an emergent pattern arising from countless molecular interactions. Could reality itself work the same way? Could spacetime be a cosmic hurricane? An emergent phenomenon generated by deeper informational processes? If so, then everything familiar, distance, location, movement, perhaps even causality, may be secondary features rather than primary truths. The implications are profound. Because it means the universe is not merely stranger than we imagined. It may be stranger than we are capable of imagining. And that realization brings us to the edge of modern knowledge. A place where science meets mystery. Where mathematics meets philosophy. Where certainty gives way to possibility. And where some of the biggest questions remain unanswered. For now, we've reached the frontier. The boundary between what we know and what we don't. But one final chapter remains. In Part 5, we'll explore the strongest evidence supporting emergent spacetime, the biggest criticisms of these theories, whether consciousness plays any role in the story, what future experiments may reveal, and ultimately, whether space truly is an illusion, or whether we're misunderstanding something even deeper. Because the final answer may be the most surprising revelation of all. To be continued. Chapter 22, How much of this is actually true? After everything we've explored, it's time for an important question. How much of this is established science? And how much remains speculation? Because whenever ideas become this extraordinary, it's easy to lose sight of the difference. Quantum entanglement is real. That is not speculation. It has been experimentally verified countless times. Bell tests have repeatedly confirmed predictions that once seemed impossible. Quantum teleportation is real. The holographic principle is a serious area of theoretical research. The relationship between information, black holes, and spacetime has become one of the most active fields in modern physics. Those are facts. But other ideas we've discussed remain open questions. Does spacetime truly emerge from entanglement? Possibly. Do wormholes and entanglement represent different descriptions of the same phenomenon? Maybe. Is the universe fundamentally informational? Many physicists think so. Others disagree. And that's what makes science beautiful. Science is not a collection of beliefs. It's a process. A relentless attempt to separate reality from illusion. Every theory must survive evidence. Every claim must survive scrutiny. Every idea must face experiment. And right now, humanity stands in a fascinating position. We have clues. We have equations. We have astonishing discoveries. But we do not yet possess the final answer. Not even close. The mystery remains open. And perhaps that's exactly what makes it so exciting. Because the next generation of discoveries may completely transform our understanding of reality. Chapter 23, The critics have a point. Whenever revolutionary ideas emerge, skepticism follows. And skepticism is healthy. Many physicists remain cautious about claims that space emerges from entanglement. Why? Because extraordinary claims require extraordinary evidence. Some researchers argue that current theories rely heavily on elegant mathematics but lack direct experimental confirmation. Others point out that multiple interpretations of quantum mechanics remain viable. And some warn that we're still missing crucial pieces of the puzzle. These criticisms matter. Because physics has experienced false leads before. Beautiful theories have failed. Promising ideas have collapsed. Elegant equations have turned out to describe realities that simply don't exist. The universe doesn't care whether a theory is beautiful. It only cares whether the theory is true. That's why experiments remain essential. Theories can inspire. Mathematics can guide. But ultimately, nature decides. And so far, nature has not delivered a definitive verdict on emergent spacetime. Not yet. Still, something interesting keeps happening. Different branches of physics continue converging towards similar conclusions. Quantum information. Entanglement. Geometry. Black holes. Spacetime. Again and again, they seem connected. Perhaps that's coincidence. Or perhaps it's a glimpse of something deeper waiting to be discovered. Chapter 24, The next experiments that could change everything. Imagine living during the era when Galileo first pointed a telescope toward the sky. Imagine witnessing the first discoveries that shattered humanity's ancient view of the cosmos. We may be living through a similar moment right now. Around the world, scientists are building increasingly powerful tools. Quantum computers. Advanced particle detectors. Gravitational wave observatories. Space telescopes. Black hole imaging projects. Each one offers a new way to investigate reality. Quantum computers are especially intriguing because they manipulate entanglement directly. Every improvement gives researchers deeper insight into the strange informational structures hidden beneath quantum mechanics. Meanwhile, black hole research continues accelerating. The first image of a black hole shocked the world. Future observations may reveal even more. Perhaps clues about quantum gravity. Perhaps evidence supporting holography. Perhaps something completely unexpected. History suggests the biggest discoveries often arrive from directions nobody anticipates. And if spacetime truly emerges from entanglement, future experiments may eventually expose the mechanism. The invisible architecture beneath reality. The hidden framework generating the universe we experience. When that happens, physics may undergo another revolution. One as significant as relativity. One as significant as quantum mechanics. One that fundamentally changes humanity's understanding of existence. Chapter 25, The Question of Consciousness. Now we arrive at a question that fascinates millions of people. Consciousness. The experience of being aware. Of seeing. Feeling. Thinking. Existing. Some people hear about quantum physics and immediately wonder. Does consciousness create reality? Does the observer somehow generate the universe? The honest answer is that mainstream science does not currently support such conclusions. Consciousness remains one of the greatest unsolved mysteries. But there is no scientific consensus that human awareness creates physical reality. That said, consciousness occupies a fascinating position in this discussion. Because every scientific discovery ultimately appears inside conscious experience. Every equation. Every experiment. Every observation. Our understanding of reality depends on minds attempting to understand reality. And that creates a profound philosophical challenge. Can a system fully understand itself? Can consciousness completely explain consciousness? Can observers ever obtain a truly objective view of existence? No one knows. Yet regardless of the answer, one thing is certain. The universe has produced beings capable of questioning the universe. And that fact alone is extraordinary. Atoms became stars. Stars created elements. Elements formed planets. Planets produced life. Life evolved awareness. And awareness began asking questions about spacetime, entanglement, and existence itself. In some sense, the universe is investigating its own nature through us. And perhaps that journey has only just begun. Chapter 26, What if space really is an illusion? Let's imagine, just for a moment, that these theories are correct. Space is not fundamental. Distance is emergent. Reality arises from quantum information. What would that mean? Surprisingly, your everyday life wouldn't suddenly change. You would still wake up tomorrow. Drink coffee. Go to work. Talk with friends. Watch the stars. The world would appear exactly the same. Because emergent realities can be perfectly real. Consider a rainbow. A rainbow isn't fundamental. It emerges from deeper physical processes. Yet it remains real. You can see it. Photograph it. Study it. Experience it. Likewise, spacetime may be emergent while remaining entirely real. The difference lies in understanding. Humanity once believed Earth occupied the center of the cosmos. The world still looked the same after that belief changed. What changed was our perspective. Likewise, discovering that space emerges from something deeper would transform our understanding of reality without changing our daily experience of it. And perhaps that's the greatest lesson of science. Reality doesn't become less beautiful when we understand it better. It becomes more beautiful. More mysterious. More profound. Chapter 27, The View from the Edge of Knowledge. Stand at the edge of the known universe in your imagination. Far beyond galaxies. Far beyond stars. Far beyond black holes. Beyond every map humanity has ever drawn. And ask yourself a simple question. What is reality? Thousands of years ago, we had myths. Then philosophy. Then science. Each generation pushed deeper. Each generation uncovered hidden layers beneath appearances. And every time we thought we had reached the foundation, another layer appeared. Atoms. Particles. Fields. Quantum mechanics. Relativity. Information. Entanglement. Now we find ourselves confronting yet another possibility. The possibility that space itself may not be the final layer. That beneath geometry lies information. Beneath distance lies connection. Beneath reality as we know it lies something even more fundamental. We don't yet know what that something is. But the search continues. And that's what makes this moment so remarkable. Because we are alive during an era when humanity is actively exploring some of the deepest questions ever asked. Questions once considered impossible. Questions that may redefine existence itself. Let's return to where we began. A simple but unsettling idea. What if space is an illusion? Not an illusion in the sense that it doesn't exist. But an illusion in the sense that it isn't fundamental. Over the course of this journey, we've followed a trail of clues. From quantum entanglement. To Bell's experiments. To black holes. To holography. To quantum information. To the possibility that spacetime emerges from deeper connections hidden beneath reality. We discovered that particles can remain linked across vast distances. We discovered that information may be more fundamental than matter. We discovered that geometry itself might arise from entanglement. And we discovered that some of the brightest minds in science are seriously investigating the possibility that the universe is far stranger than appearances suggest. Yet despite all these discoveries, one truth remains. The mystery is not solved. Not yet. We are standing at the shoreline of an infinite ocean. Every answer reveals new questions. Every breakthrough exposes deeper mysteries. And perhaps that's exactly how it should be. Because science is not merely a collection of facts. Science is an adventure. A journey into the unknown. A refusal to accept easy answers. A determination to follow evidence wherever it leads. Even when it challenges our deepest assumptions. Even when it forces us to rethink reality itself. So the next time you look up at the night sky, remember this. The stars may be separated by unimaginable distances. Galaxies may appear billions of light years apart. The universe may seem vast beyond comprehension. But beneath that vastness, beneath the space we experience, there may exist a hidden network of connections. A deeper reality. A reality woven together by quantum entanglement. And if that's true, then perhaps the universe is not a collection of isolated things. Perhaps it is one interconnected whole. A cosmic tapestry of information, relationships, and possibilities. A tapestry we are only beginning to understand. And the most astonishing discovery of all may still lie ahead. If you enjoyed this journey into the deepest mysteries of reality, make sure to subscribe, leave a comment with your thoughts, and share this documentary with someone who loves science, space, and the unknown. Because the universe still has secrets. And together, we'll keep searching for them. Until next time. Keep looking up. And keep asking impossible questions.